the last talk is by Paul Fendley, guided by Baxter.
Well, again, like all the other speakers, I'm greatly honored to be able to do this on the last talk. So I think I'll try and take it easy on you all, but also I wanted to make contact with Rodney's results and, how have influenced me throughout my entire career, but certainly on some of the things I'm working on right now. So I'll tell you a bit about those, but also try and put them in the context of Rodney's work. So anyway, there's a quote that probably everyone watching has seen by Mark Katz, basically saying there's two kinds of geniuses, the ordinary and the magicians. The ordinary, they're just smarter than us and can do a lot more. But the magicians, what they do just comes from nowhere, or at least as far as we can tell. And as he says, even after we understand what they have done, the process by which they've done it is completely dark. And I think Rodney, as much as Feynman, as this quote is often used to describe, Rodney belongs to this category. But what's unusual, at least to me, his style of magic is very different from any other of these brilliant physicists I've seen. I mean, he definitely didn't use physics intuition, and he definitely didn't use abstract mathematics. But I mean, applied mathematics is usually used as a pejorative term in both physics and math departments. But this is somehow what Rodney did. He saw his way through all these nasty technicalities and found all these things that just nobody knew were there. If you read his papers or his book, the beauty isn't always there, but isn't always apparent, but it's there. Anyway, so lots of things, I remember learning as a grad student, you're supposed to read the footnotes of the masters. I don't think Rodney was big on footnotes, but you have to, look through his papers and see all these nuggets that are still there, things he understood and exploited perhaps, or not exploited, but that we still really haven't incorporated into our world. And in particular, I think there's certainly many examples of this, but the one that still, I think, stands out is his solution of the 8-vertex model and the XYZ spin chain. So as again, everybody at this meeting knows, this is where he pioneered the Yang-Baxter equation and in some aspects reduced finding integral models to a cookbook. You look for the solutions of the Yang-Baxter equation, that gives you an integral model. But what I think is often forgotten is that in the absence of a U1 symmetry, it's much, much more work to get further. I mean, I can't understate that because XXZ is great. It's got a U1 symmetry, the Badon starts works, lots of things work. But for the 8-vertex model, what Rodney solved, or the XYZ spin chain, you need much more insight to get much further. I know Rodney supplied some of this insight. We're still pushing on these things, but let me mention a few before I get to the specifics I wanted to talk about. So something again that I think is not forgotten, but maybe not as well known as some of the other stuff, is when he was attacking the 8-vertex model, it was such a daunting thing. He came up with a lot of interlinked strategies, and the sort of simplest one to state is that he found another model. This is called the SOS model, but he found another model whose transfer matrix commuted with the 8-vertex model. But this model had a U1 symmetry. And then that one you can apply the Badon sots. But then you have to kind of then reverse engineer. You can find the eigenstates of this model, but then you have to reverse engineer what the eigenstates are of the original model. But he did all this. In the course of doing so, at least that's my reading of how he did it, although again, it's such an mysterious thing in that it came from nowhere. A second way he did it was to define this thing called a Q operator that comes up increasingly, I think, these days. So it's an operator that commutes with the transfer matrix, and more importantly, it obeys these nice relations with the transfer matrix. Product of TQ is Q plus Q, where there's some arguments. I decided wasn't going to write all that out because I'm not going to use it. But I want to emphasize, I mean, that again, just absolutely as far as I can tell, came from nowhere. This was, it's some of it is better understood now because of quantum group algebras and all that. But again, remind people this works for models without a U1 symmetry like the 8-vertex model. So again, we've learned a lot more about Q operators. Ed Witten mentioned in his talk the other day a very novel interpretation coming out of Kevin Costello's work. They can view as at Hooft lines in 4D Chern-Simons gauge theory. The TQ equations then come actually rather simply. The setup requires a fair amount of work, but then the TQ equations in that context come from the effect in gauge theory with monopoles called the Witten effect. But I think it's fair to say, I'll say I don't understand the Q function and where it comes from and what it means. Maybe others do, and you can illuminate me later on. But I find it still mysterious. Certainly, if you look at the original papers, it's just this genius of Rodney to pull things out of nowhere. And it's nasty technical. It's not like the minute he pulls something out, you go, oh my God, that's so simple and beautiful. Rodney, his genius was in the technical. So there is something that is a little bit easier for us mortals to comprehend, and it's the analogous T and Q that come up in conformal field theory, a beautiful series of papers by Vladimir and collaborators, Sergey and Sasha. But anyway, so there's a T and Q that are very analogous. They satisfy analogous relations. But conceivably, they're the continuum limit of Rodney's Q or some of Rodney's Q. The catch is Rodney had multiple different definitions of Q. So who knows if the BLZQ is a limit of a lattice one. I don't know it. Maybe again, people can illuminate me, but it's not obvious. But then this T and Q, because it's in field theory, so it's maybe a little bit easier to understand because it's a little simpler to grasp. But it's now come up in a bunch of really far removed cases. Ones where I'm surprised. This beautiful result of Doreen Tateo relating this to spectral determinants for ordinary differential equations. This turns out actually, if you want to actually compute the T and Q of Bazhenov-Lukian and Samolechkov, I think it's the simplest way. You just solve the appropriate Schrodinger equation on the computer and computed spectrum, which is now all easily done. And then computed spectral determinant and Doreen Tateo tell you how to relate that to this T and Q. So in something that, again, we were mucking around with similar things at the time, and again, something else that may be forgotten, this T and Q of Bazhenov-Lukian and Zamolodchikov is just simply the partition function of the boundary sign Gordon model. So a famous version of what people call quantum impurity problem. And then T, what's the transfer matrix in the original Baxter setup, is the partition function thing. I should say these are the eigenvalues. T and Q in this thing are the eigenvalues of these operators as well as they. And actually, another thing that I always found very beautiful is that a certain point of T, if you set the coupling correctly, gives the order parameter statistics of the critical Ising chain. So I hope no one would argue with me. The full significance of these TQ relations is just far from understood. I mean, I'm confident they'll come up again in yet another context soon. So again, reading the original papers is a good idea. It takes a little time, but it's worth it. And so now I'm going to start to segue into some of the things that, the newer things that I want to tell you about. But again, to stick with the 8-vertex model of XYZ chain, which I'm going to do for a bit, it's a canonical example of an elliptic integrable model, where the Boltzmann weights are written in terms of elliptic theta functions. And I'll say a little bit more about what this means, but I think, again, this is ground ripe for work because it's just much harder. One of the things I find very tantalizing about Kevin Costello's work that Ed Whitten talked about the other day, is that in that framework, getting these elliptic integral models is more natural. And in lots of other frameworks like quantum group algebras, it's much less natural. Anyway, so again, the lack of the U1 symmetry makes finding exact eigenstates extremely difficult. Now, there's been a news story. People have been thinking about it in the scars, for example, that Fabian mentioned. Maybe Andreas Klumper mentioned this, but I was asleep when he gave his talk. But Rodney in his original paper found what are now called helical states. So again, via this somewhat complicated construction that I mentioned before, you have to get the beta ansatz. So beta ansatz needs an exact eigenstate. That's why the U1 symmetry is so useful. It's useful because then if you have a U1 symmetry, you can find the fully polarized state and use that to build the beta ansatz off. But since without the U1 symmetry, those aren't obvious, but nonetheless, Rodney found these helical states that allow the beta ansatz to be implemented. And these are very much ancestors of what people now call quantum scar states. So again, just reemphasizing the point that there's a whole beautiful formalism there that still needs fleshing out. So again, another thing that Rodney did to make some progress that I'm not going to say anything about is this corner transfer matrix. That one's a complete mistake. Okay, but so I'll get mysterious at the end again, but I want to bring the discussion back down to earth and see how far we can get with less technical methods. And my style is very, very much, I think, the opposite of Rodney's, in that I try and make everything as lowbrow as possible and avoid technicalities as much as possible. You have to read the technical papers and then stare at them and see if I can get with lowbrow stuff. So I'm going to tell you about some new work that I think is lowbrow, but in a good way. So, okay, so now let me be a little bit more concrete. Probably everybody here knows, but just in case, let me remind you what the XYZ spin chain is. So this is closely related, I'll explain in a second why, to the full 8-vertex model that Rodney solved. And so we have a Hilbert space of L2 state systems, and we define the usual Pauli matrices that act on the Lth site. And so we have, I'm going to define 4 to the L Pauli matrices because, let me make a pointer here now that I'm being more concrete. So I'm putting 4 indices, just the Pauli matrix with 0 label is just the identity. So anyway, the XYZ Hamiltonian then is the usual nearest neighbor form with 3 couplings. There's no U1 symmetry, or no obvious U1 symmetry, I should say. So a fact that people may have forgotten is even before Rodney made his magnificent solution of the 8-vertex model, and hence the XYZ chain, Sutherland had noticed that this Hamiltonian commutes with the 8-vertex transfer matrix. So already that's a strong hint that the model is integrable. And then, sorry, I should say an 8-vertex transfer matrix. If you define an 8-vertex transfer matrix appropriately, Rodney, and then Sutherland showed that they commute, and then and they commute for a family of couplings. So already that basically says that the XYZ spin chain must be integrable. I think it says, but anyway, we'll come back to that. But then Rodney did his magnificent work after that. But what, again, I said I'm trying to be lowbrow. Maybe I'm always lowbrow, but we don't need to know anything about the 8-vertex model to make progress on this, which are the new results. So I'm going to talk about a pair of papers that will come out pretty soon. I think I'm usually bad at getting papers out, but luckily I have collaborators that are better at it than me. So there's a pair of papers. The one I'll mostly talk about today is with Sasha German, Eric Vernier, and Frank Verstrada. There's a closely related one with Fabian as well. So but the point is, you can see that the XYZ Z-spin chain is integrable by really elementary computation. And so, which again, I think bodes well for future studies of this model, and I'll tell you about how that goes. So in particular, we construct a generating function for conserved charges, or what people sometimes call the higher Hamiltonians if you take the logarithmic derivative. But in terms of a matrix product operator, and if you don't know what that is, I'll tell you on the next slide. And the trick, this is a bit opaque comment, but for those of you who know, the trick is to first take this interesting operator that I found called the strong zero mode operator, and you write that in terms of matrix product operator, and then you push it a little further and you find, well, what I'm about to tell you. Okay, so let me first just tell you, this is just total review. Matrix product operators have, because of all sorts of marvelous progress in the quantum information approach to quantum many-body systems, people have begun to think about the systems that we study in slightly different ways. Yeah.
Just a minute, Andreas has a question.
I have a question. I mean, you said you construct a matrix product operator as a generating function for the conserved charges, but the transfer matrix itself is a generating.
Well, yeah, no, is it right? I construct a simple. I should have said a simpler one, and by elementary means.
Okay.
I mean, no, Yang Baxter. I'll get to that. I'll ask that question again if you. Yeah, so of course the transfer matrix can be written as a matrix product operator. I should have put nice. Simpler. How about simpler? Much simpler operator. So I'll get to that. Right. So anyway, so the matrix product operator, let me say MPO, it's shorter, is built. So the way you write it, this is the canonical form of such a thing, is you have four matrices. I haven't said how big the matrices are yet, but this is just the generic form. And so, oops, don't want to do that yet. So anyway, so the A's are the matrices, the S and the T are the labels of the matrices. And so these are the Pauli matrices acting on the chain. That's why I made the identity one for the R equals 0 be the identity, because then I can basically write any Hermitian operator acting on this chain, no matter how non-local, is a sum over these things. Now, we're not writing an arbitrary operator. We're going to pick a particular form for the coefficients, which is the product of these matrices. And S and S prime are the matrix things at the end. So we have a family of these operators. Then we multiply the matrices along the chain. There's a really useful picture for these things. So this is now the matrix times the operator. We would draw this. The R represents the operator acting on the Hilbert space, the Pauli matrices, and then the coefficient is this operator here. This dangles at the bottom to emphasize it's an operator. If you've seen what matrix product states are, you stop that there. So indicate that's not an operator, it's a state, but this is an operator. So it has a dangling end there at the bottom. And then this thing is just multiplying these matrices all along, going from, in my conventions, from left to right. And this is the coefficient of the operator, and the A's and then the sigmas are the operator. So that's all, everything I just said here is completely standard. We can now write the Hamiltonian in terms of these pictures too. It's a sum over terms. So the Hamiltonian, remember, is just nearest neighbor interactions, and that's what's in this. I was going to say black box, but I guess I made it a green box. So inside the green box is the sigma xj plus 1 times jx plus the other two terms. And that's how we would draw that. And so now what we're going to do, so I emphasized Andreas's question and to, again, but I'll say it again. We're going to do something very lowbrow here. And we're going to say, let's look, armed with this, we're going to look for a matrix product operator expression that commutes with XYZ. And I said, of course, the transfer matrix does, we know, but I pretend I don't know that. And in fact, we can find a conserved charge by demanding a solution to the following equation. So what this is, finally. So we take, these are operators now, not states. So we take the Hamiltonian just for two sites, so the two-site Hamiltonian, that part of the Hamiltonian, and we multiply it times the matrix product operator. But of course, we can do this in the reverse order and look at a commutator. So that's the left-hand side is this commutator there where I omitted all those indices to make it look easier. These are just the A's on that and the sigmas, which I should have put in, but the sigmas are implicitly there. And commute that. Now, obviously, if it just commuted, we would be done, but that's pretty easy to see. There's nothing so simple. But what we can do is if we have something that the right-hand side is much simpler, then we can get a matrix product operator. And the simplest form that does this, there's more complicated ones, but the simplest form that does this is the following. We have some other matrix E, any matrix E here, where a matrix product built from that. And if it satisfies this, where it's the same E on the right and the left, then you get a solution. Then if this does, well, then for periodic boundary conditions, if you have a solution of this thing, well, then you just sum up, well, H is the sum of all the terms in the Hamiltonian, but then O is the product. And then you see as you act with the Hamiltonian all the way down, these things cancel. This one will cancel with the Hamiltonian coming from the next two sites and so on. And for periodic boundary conditions, these just cancel completely. We have to be a little careful with the boundary. And so we sum over the subscripts on the O from the previous slide were just what happens at the end. So basically we're taking the trace of this product of matrices and you get something. So I wouldn't be telling you this if I didn't find something nice. We didn't find something nice. And indeed, you just plug the XYZ Hamiltonian and you look in the right place and there's a solution. So let me tell you what that solution is. It arises from a 4-channel matrix product operator. But the point is, it's really simple. There's no elliptic functions. There's no anything. So that's the answer. It's these very sparse matrices. And moreover, we have a 1-parameter family of them. So the point is we then have a 1-parameter family of conserved charges. And moreover, this matrix product is much simpler than the 8-vertex transfer matrix. So that was Andreas's question. Well, the 8-vertex transfer matrix I can write as a matrix product operator. Sure, but it's much, much more complicated. The point being, because if you look at the form of this here with these indices here, anytime you have a sigma k, well, the next one down the line has to be a sigma k. And well, they have to come in pairs, and then same with the sigma, the next one, and then if there's sigma x, whatever, and all that form. So that's much, much simpler. And the coefficients are elementary. And this V is the spectral parameter. Well, it's related to the spectral parameter of X, Y, Z. This one, it isn't. Sasha worked out what it was. I forgot. I should have written down the formula for the usual spectral parameter. But again, you never need any elliptic functions unless you want to relate it to the other stuff. So this formula, this MPO involves Jx, Y, J, Z directly. There's no elliptic functions. And like I said, just reiterate this, since we have a one parameter family of commuting operators, it generates a sequence of conserved charges. An interesting thing, if you look at them explicitly, I don't think it's anything new. It's hard to prove for the higher order ones, whether they're all subsumed, but it looks like it's half of the ones you would ordinarily get from the Yang-Baxter equation, but half of infinity is still infinity. So this shows, maybe not quite rigorously, but pretty convincingly, the model is integrable, even if you didn't know about the 8-vertex model. And now the payoff on this is you can do things that were hard, requiring solutions of boundary Yang-Baxter. So if you just add arbitrary boundary magnetic field to the Hamiltonian, you just can you modify the MPO a little, you put some vectors at the end, instead of taking the trace, for which you do for periodic boundary conditions for the coefficients of these operators in the MPO, you just sort of put it off, cut it off at the end with some matrix, but then you look for these equations. Again, the simpler equations, but the simple equation for these B, the things you don't know, the thing in the MPO is just a linear equation. So it's really easy to solve because the E and the A have to be the same ones that worked in the bulk. That's what's nice. This reduces this integrability thing to something local, like the Yang-Baxter, but it's simple. It's simpler than the Yang-Baxter. And so it's sort of an elementary calculation to then get the commuting charges even in the presence of an arbitrary boundary magnetic field. And now we can push this further. I didn't write this down, but we know how to do the MPO for anisotropic, but still integrable couplings. And then you can take the spins at the edge and then glue them to the edge. That's still then a more complicated boundary, and then just crank out all the boundary conditions you want. So, anyway, so a few more comments. I'll go back to schematic mode. And so one thing, this is related to the 8-vertex transformation, but not in any obvious way. It's the product of two of them, but that's not obvious from the form. So what, if you like the 8-vertex model, you say, well, it turns out you take the product of two 8-vertex models and where the spectral parameters are related in a very special way. And the product is much simpler than you might have thought. We know how to do that and get the identity or get some other simple things, but this is not as simple as that. So that's very curious. I don't know quite what that means, but it's true. Some things that we're thinking about now, maybe you can ask me more about it. I thought I would just flash this. There's some more things to say, but that's very much work in progress. So good. One comment though, I mentioned this Q function. I mean, this is some operator that commutes with a Hamiltonian, a nice one. It's much nicer than the usual Q function, but I don't know what it has to do with it. That would be an interesting thing to try and understand. Okay, so now let me go back to general. So one of the morals I take from this, and actually a variety of other things, is there's really, Rodney's work is magnificent, but it certainly didn't end the story. And people who know me have heard me rail against this idea that now everything was done in the 80s and with the development of all these beautiful quantum group methods. I think all those things, Rodney's work and the quantum group work, just point to a host of even more difficult problems that we should hopefully can solve. And I would be remiss if I don't know if anybody, well, I've missed a lot of the talks because I've been asleep, but if anybody mentioned Karl Potts other than Chico, last night for me, or anyway, so again, just to say a few more things that I find that people should, I would hope people do. This magnetization in the chiral Potts model, there are all sorts of hints that there's some more structure there. This free power fermion story that Chico mentioned this morning, there's certainly more there. And all these hint that whereas Yang-Baxter methods are essential and basic, there's lots more out there. Let me just quickly go through some other questions that I randomly assembled, at least that have always intrigued me. And if one of you gets interested in by any of this, worth making this slide. So this corner transformation I mentioned briefly. I mean, why does this work? I don't know. It's a beautiful analyticity thing. That's what Yang-Baxter gives us, is a form of analyticity, but it's still magical. 3D integrable models, again, Rodney's papers, in particular ones he wrote with Vladimir a long time ago. Again, there's so many intriguing things that I think haven't been exploited. Again, this to harp on elliptic integrable models. We know about quantum groups and for trigonometric integrable models, which tell us an enormous amount of stuff, but very little is known about the elliptic case. So there are the things people have tried and people have said something interesting, but some interesting things, but there's so much there. And again, just to restate this absent U1 and a problem. So there's this model, again, Chico mentioned, this model I study which I called free fermions in disguise. So I invented all this trickery to make it look like free fermions. But if you take periodic boundary conditions, the construction I gave again easily gives the fact that the periodic case remains integrable. It's simpler than even the XYZ calculation I mentioned. But I don't know how to solve it. I'm not as good as Rodney. I can't see through the technicalities, so I don't know how to find the solution for the periodic case. I don't know what the analog of the 8 vertex model, or if there even is a nice one like that. Anyway, well, thanks so much to Murray and Vladimir for organizing this great meeting, and it's such an honor to be here, and thank you all for listening.
Questions?
Maybe a comment. I would like to add that Baxter's basis states he constructed in 1971, these spin helix states, are not linked to the magnetization operator, as you indicated, but they show some conserved properties. The Hamiltonian of the XYZ chain acts on these basis states by preserving the number of kings. These spin helix states can be understood as a succession of rotations in forward and sometimes in backward direction. And the backward direction that defines, one can say, kings, and the number of kings is preserved. But the kings are pushed to the left or to the right. So there's still the local action of the Hamiltonian of the XYZ chain on these states, and the total number of these kings is preserved. So there is something which is preserved in the 8 vertex model or in the XYZ chain, but what is preserved cannot be understood as an eigenvalue of an operator. I think that's the trouble.
Yeah, that's why I think I amended my statement. There's no obvious UN symmetry, because we know from at least the field theory thing, because it's at least in the field theory limit, it becomes Sine-Gordon model. And again, we have kink number there. So there's a hidden U1, but I've tried and failed over the years to find some nice lattice operator that gives this in any model of this type. And either there's an obvious one, or but in this case, at least I never found. But yeah, absolutely. And maybe thinking about these helical states again 50 something years later is will shed some light. But I agree. Yeah, I agree with everything you said.
So we have an online question. Go ahead.
Yes. Hi, Paul. This is Tomasz.
Hi.
I wonder whether you can get local charges out of your construction. So do you have any idea how you get, if you can get local charges by doing some manipulation like log derivative of the order?
Yeah. So, right. Yeah. So this is why I said every other, because you can just check. It gives the same, it gives, at least at low orders, every other local Hamiltonian you get just by taking the log derivative.
Right.
And what's curious is, those are just the same ones, so they're nasty. But so what it says, there's a generating function, or what it implies, I haven't proved this for all orders, implies there's a simple generating function for half the local Hamiltonians. And they say that because of this restriction I mentioned with, the types of operators that appear, that's much simpler than even in the third local Hamiltonian. So you see, for example, so you expand it out, you take the logarithmic derivative and expand it out into powers. And so the next term is just h squared. I remember when I did this, it's like, oh God, this is going to be depressing. It's just going to be the exponential of the Hamiltonian. But then you go to third order and you see it's not h cubed. But h cubed is actually much nastier than this operator. And so when you subtract h cubed with the right coefficient from this MPO at third order, you put in, it cancels the non-local terms, but then puts in all these nasty local terms. So they're there, but I don't know a closed form. There's one intriguing thing. There's this work by Bernard Nienhuis from a few years back, and collaborator, about writing the conserved quantities in terms of the Templey-Lieb generators. And I would love to be able to, and there is someone, sorry, I can't remember who, did a generalization to XYZ, but it's not so nice. The XYZ one, the XXZ one that Bernard did with the temporary leap generators was really nice. And my fantasy would be that there's something equally nice for XYZ using this MPO, but I haven't found it yet.
Can I have another question?
Yes, go ahead.
So, I mean, I have another question is also like a kind of comment. I mean, you restrict yourself to 4x4 auxiliary space, right? Or to 4-dimensional auxiliary space, right? So you didn't have to do that. I mean, you could just explore other solutions of your southern length relation, right? And I want to make a comment. I mean, with Slava Popkov, we have a paper a couple of years ago on XYZ with boundary dissipation. And when you look for solutions of Lindblad's equation with boundary dissipation, you basically are solving the same problem. But we've got also solutions for that, which are not finite dimensional, but they are kind of three diagonal infinite dimensional matrices. So it would be nice.
Good. Yeah, no, I absolutely. The reason
Yeah,
for
but-
4 was this
Yeah.
this comment I made about the strong zero mode. That one
Yeah.
had 4 channels needed, and so then you went there with that. But I agree, it fits in naturally, the 4 channels, because there's 4 Pauli matrices, if you wish, including the identity. And
somehow
so
you restrict yourself to some symmetry sector.
yeah,
which only-
yeah. So, but I completely agree. And in this paper that I mentioned but didn't talk about with Fabian and Eric, so we do higher spin versions, and that's clearly an issue, that the number of channels. So we can find 4-channel versions, but then there's clearly also other ones there too. And so it then turns into a zoo again. And
I guess you will get quasi-local charges when you
yeah. Right. No. So you do. But things still simplify, at least if you look in the right place, and maybe that's the moral. If you look in the right place, these things get remarkably simple. And I think that, well, I think that's a new comment on things.
Okay, thanks. Very interesting. Yeah, thanks.
Thank you.
Let's thank the speaker again.
And let's thank the organizers again. It's been really great.
Once. Yeah.